Hello everyone. Welcome to our presentation on a constant factor approximation for the capacitated min-max tree cover problem. I am Lavina Jain from IIIT Delhi. This is a joint research with Dr. Samantak Das from IIIT Delhi and Nikhil Kumar from IIT Delhi. Let me start by giving a background of the problem. Covering vertices of a given graph using simpler structures like paths and trees have long attracted the attention of computer science and operations research communities. One classic example is the nurse location problem. The goal is to place a group of nurses at different locations and finding a tour for each one of them so that every patient is visited by a nurse. Similar setting arises in vehicle routing problem. Suppose we are given a set of vehicles initially located at a given set of depots. The goal is to find a tour for each of those vehicles, each starting and ending at their respective depots so as to cover client demands at various locations. One of the most popular objectives is to minimize the maximum distance traveled by any vehicle, also known as the make span of the solution. A standard reduction shows that this problem is equivalent within an approximation factor of 2 to finding trees in a graph such that all vertices in the graph are covered by the union of these trees. In this paper, we consider a natural generalization of this setting. Moving on to our problem statement. Given a graph with edge weights and parameter k, we are required to find a tree cover with k trees such that the maximum cost of a tree in the cover is minimized. One important point to note here is that we need to find a tree cover and not a partition. The trees can have overlapping vertices as well as edges, but each vertex is covered by exactly one tree. Like in the given example, the node A belongs to both the green and the blue tree in the cover, but it is only covered by the green tree. We have solved a capacitated version of the problem, where in addition to the parameter k, we are also given a parameter lambda. We are then required to find a tree cover with k trees such that each tree covers no more than lambda vertices and the maximum cost of a tree in the cover is minimized. Like in this previous example of min-max tree cover problem, this was the graph and this was the cover. In this, the maximum vertices covered by one single tree is 5 in the case of the green tree. But when we're talking about the capacitated version, let's say the lambda was 3 here, so each tree cannot cover more than 3 vertices. We also solved the rooted case of the capacitated min-max tree cover problem. Here, we're also given a set of roots, and each tree in the cover has to be uniquely rooted at one of the given roots, like shown in the example. Known bounds and related work. For the uncapacitated version of the problem, the known approximations for the rooted and unrooted case, respectively, are 4 and 3 by Even et al. In 2004 and Khani et al. In 2014. For a specific version of capacities, that is, fixed capacity of lambda for every tree, the approximation known for the unrooted case is 2k minus 1, where k is the number of trees in the tree cover. This was given by Gutman-Beck et al. In 1997. All these different versions of the problem are proven to be 3.5 approx hard. In this paper, we give the first constant factor approximation for the capacitated version of the min-max tree cover problem for both rooted and unrooted cases. The approximation factor for now is quite large, but we believe that it can be improved by close observation. Now, we start off by discussing high level ideas and techniques used in the paper. For the purpose of the talk, we will present the algorithm for getting a tree cover with trees covering exactly lambda vertices. This can be extended to the capacitated version by using simple ideas presented in the paper. The first technique is guessing the cost of the optimal solution. Call it T star. This is the maximum cost of a tree in the optimal solution. The guessing can be done by binary search on the range. Then we remove all edges with cost greater than T star because no such edge can be a part of the optimal solution. We can be left with multiple components. We then treat each of those components as a separate graph, run our algorithm, and then combine results. In the given example, the graph turns into two different components. A question that may arise is that we do not know the separate case for these components. But the way that we run our algorithm, we do not explicitly need to know the value of k. This will become evident in our procedure ahead. The second technique is using the MST of the graph as a lower bound. Let us look at the optimal solution. All the k trees have a maximum cost of t star each. We can add k minus 1 edges of cost no more than t star and get a spanning tree. Hence, the cost of MST is upper bounded by 2k minus 1 t star. This leads to the natural idea of starting with the MST of the graph. This brings us to the third high-level idea. We could start with the MST, pick an arbitrary route, and then traverse it bottom up starting from the lowest leaf, while chopping off subtrees when their cost reaches between 2t star and 4t star. Now, if we try to apply this to the capacitated version, what is the problem? A potential problem is that we have no control over the structure of the MST. In particular, some part of the MST might be too dense. It might contain a connected subtree that has a small length but covers a large amount of vertices, while some other parts might be too sparse. Hence, cutting off the MST on the basis of cost might end up producing infeasible trees with too many or too little vertices, although the cost might be bounded. To tackle this problem, we utilize the concept of lambda MSTs. Given a graph G, a lambda MST on G is the minimum length subtree of G which contains exactly lambda vertices. We observe that each tree in the optimal solution covers exactly lambda vertices, and hence opt can be thought of as a union of k lambda MSTs, although not necessarily of the minimum possible cost. With this, we have reached the methodology. We start off with an arbitrary route and construct a lambda MST around it. Since construction of a lambda MST is NP hard, we use a known 4-approx algorithm. We continue the process of picking an arbitrary vertex and constructing a lambda MST until either there are no vertices left or the remaining vertices cannot be connected into a tree with low cost. Now, why can there be such vertices left? Let us look at an example. When we construct a lambda MST, in the good case, we construct a tree from the optimal solution. But in the unlucky case, we might pick vertices from different trees of opt and combine them into one tree. Due to this, we can be left with vertices such that there does not exist any lambda MST of low cost that can cover them. Like in this given example, if this is the optimal solution and we picked this vertex to start making the lambda MSTs, in the good case, we could make this tree which is actually an opt tree. But in the unlucky case, we might end up making this tree which leaves this vertex out. And we can subsequently make these trees which leave more vertices out that cannot be combined into one tree now. For now, we will call the lambda MSTs we have constructed as good trees and the trees that are left behind as bad trees. And we will try to solve this problem with the constructive iterative process. Now, we look closely at the bad vertices. Some of the bad vertices can be combined with each other to form high density, low cost trees. We run an uncapacitated K tree cover algorithm on the bad vertices to combine them into such trees. Let us call these trees as bad trees. Now, the essential idea is to connect some of these bad trees to the existing good trees, such that the cost of any one good tree does not increase by a large amount. We create a bipartite matching between these bad trees and good trees. In the bipartite graph, there is an edge between a bad tree and a good tree if the smallest distance between the two is no more than t star. A point to note here is that there will be no such bad tree which has zero outgoing edges. Now, why is that? Notice the optimal solution. Each of these bad vertices are a part of a tree in opt, and hence, if there is no good tree close to such vertices, this means that there should have been one more lambda MST covering this optimal tree. In this bipartite graph, we really want a perfect matching from left-hand side to make sure we do not connect too many trees to any one good tree. Since we do not control how bad trees are formed, there may be Hall sets in the graph. For example, here, bad trees 1, 2, and 3 form a Hall set. We run a uncapacitated K tree cover algorithm on these, and they recombine into bad trees 1 dash and 2 dash, which can now be matched with two good trees. We will iteratively pick each Hall set and run the MMTC algorithm on them again. As a result, one thing which is not clear is why will the process terminate? Each time we run the MMTC algorithm on a Hall set, we reduce the size of the set to that of its neighborhood. Hence, the process will terminate in finite time. Now, why is it even possible to reduce the size of a Hall set to its neighborhood? We claim that the number of optimal trees that the vertices in the Hall set were a part of cannot be more than the size of the neighborhood of the Hall set. I will repeat this one more time. We claim that the number of optimal trees that the vertices in the Hall set are a part of cannot be more than the size of the neighborhood of the Hall set. Like in this example, the vertices of bad trees 5, 7, 8, and 9 are covered within two optimal trees, because otherwise we could have made one more good tree and the neighborhood of the set would have been 3. Now, since these vertices are covered in two optimal trees, they can be appropriately recombined into two trees of cost within a constant factor of t star. That is why we are able to reduce the size of the Hall set to the size of their neighborhood. This way, we keep on resolving Hall sets and ultimately reach a perfect matching of bad trees and good trees. We have succeeded in creating k sufficiently dense trees with cost of O of t star. What is left is to split and reconnect these trees to make k trees with exactly lambda vertices each. For that, we contract good trees into nodes. In the first graph shown, the nodes represent the good trees. There is an edge between the nodes if the smallest distance between the trees is less than t star. Again, the graph will be connected because we removed all edges of cost more than t star earlier. We then create a Hamiltonian path in this graph by connecting vertices up to a distance of 3 edges. Notice in the second image that the distance between the node A and B is 3 edges. Finally, when we have a path, we will start splitting these nodes, which are actually good trees, as soon as we cover lambda vertices each. Since there are exactly k lambda vertices in the graph, this will result in k trees with lambda vertices each of cost of O of t star. To summarize, we have proven the constant factor approximation algorithm for the fixed capacity case of the min-max tree cover problem. Our results extend to the capacitated case, where each tree can have at most lambda vertices instead of exactly lambda vertices, as well as the capacitated multi-rooted case, where given a set of roots, each tree has to be rooted at a given root. I request everyone interested to have a look at our paper. The key takeaways from our paper are the two techniques. One is starting with the lambda MSTs instead of an MST in the capacitated cases of the graph problems. This helps in controlling the number of vertices in a tree cover. The second one is the iterative refinement procedure that distributes vertices as evenly as possible among the different trees in the cover without incurring too much cost. I would like to end with the open questions related to our problem. We believe that the approximation ratio can be improved by creating an LP with a constant integrality gap, which is not known even for the uncapacitated case. The other open problem is proving a p-TAS for the capacitated versions of the MMTC problem on special metrics like the tree metric. That is it for our presentation today. We hope our ideas would encourage further research in the problem. Thank you so much for your time.